Hello. Can everybody hear me okay? All right. Welcome to my talk, Visual Diagnostics at Scale. And so this is going to be a yellow brick talk. Show of hands, people who have used yellow brick before and know about yellow brick? Okay. So actually, I think we might have some other contributors here in the audience, because that's probably why they're cheering. But this is a slightly different flavor of yellow brick talk. I've never given this talk before, so it's a little bit of an experiment. So come along with me on this journey. Generally, I think at a high level, what this talk is about is who is yellow brick for? And really the question of scaling, I think, is about really kind of making choices about affordances for some users and not for other users. And so that's kind of what this talk is sort of really going to be about at a high level. So my name is Rebecca, and among other things, I am the creator, together with my partner in crime, Benjamin Bengfort, of the Python library Yellowbrick. So Yellowbrick is a pure Python machine learning visualization library. It's built on top of matplotlib, which, and it got a little shout out, I don't know if it had a little cameo in yesterday's tools update talk about third-party matplotlib packages. So Yellowbrick is one of them. And it's designed to work with scikit-learn style estimators and transformers. And so, you know, I think that if you haven't checked Yellowbrick out yet, I'm going to show a little bit of it today, but I would suggest checking out the documentation because it's a lot more than I can sort of cover. But if you want to also find me on social media or GitHub or whatever, I'm very discoverable. I use the same handle for everything. You know, I feel like a generalist in a sea of experts, a little bit. I am not I don't think I sort of self-identify as a scientist. Maybe I'm a data scientist. But I really, I work in industry, and I've worked in a lot of different industries. And so one of the things that I sort of wanted to start with is to contextualize some of these kind of visualization at scale type questions in the context of some of the data that I've worked with. And I've worked with a lot of really different data sets. I've been sort of lucky, sort of opportunistic, and gotten to experiment with a lot of different kinds of data. And so when we talk about scaling, I think it's important that we talk about kind of specifically what does that look like for different kinds of data, different kinds of work. So, for example, when I was at the Department of Commerce, we would routinely work with data sets, where maybe there would be on the order of a couple of 100,000 instances, by which I mean, rows, and then maybe 50 features, by which I mean kind of the columns, right? And these would generally be, categorical type features, similar to the ones that Alan was talking about in his talk a little earlier this morning, things like age and gender, occupation. Before Commerce, I worked at OSHA, the Occupational Safety and Health Administration. In that case, data, often was very, very different. So for example, imagine, a sensor data set that's coming in on in a streaming fashion. And what you're getting are, maybe every 5-second or every 30-second readings of the amount of ammonia or toluene in the air at a nail salon, because that is that's unhealthy to be inside an environment with a lot of toluene, for example, especially if you do it all day long. Now I do natural language processing, somewhat like what Rachel was talking about this morning, but hopefully less terrifying. So like a very good example of the kind of practical stuff that people will sort of pay you to do NLP for is building a classifier to detect sarcasm. Right, because it is certainly a concern, the ability to detect bots in social media conversations, but it's also important to be able to detect sarcasm, because if somebody says like, I love the new Android phone, that's really different from I love the new Android phone, but those words are identical, right? So that's really hard to model, but it's also very valuable if you can kind of model that sort of stuff. And in this case, maybe we even have fewer instances than the other two data sets, right? Maybe I only have 50,000 labeled instances because I could only get the interns to label that many for me. But in terms of the feature space, in terms of the dimensionality, it's massive, right? It's not unusual for me to work inside a feature space of like 10,000 features or 5,000 features. And in this case, the features are things like words, right, or emoji, or sometimes timestamps and stuff like that. So these, scaling insight for these different kinds of data sets is really context specific, right? So when people sort of think about like, oh, haven't we sort of solved machine learning? Can't you just put it into a black box? It's sort of chuckle, right? Because there's so much kind of complexity. Scaling this kind of stuff is really, really hard, and it takes a lot of domain expertise to even have an intuition about how to go about modeling data in a lot of cases, as I'm sure all of you are very aware, because many of you are domain experts. So you can have a problem of many, many features. It can be big data in the sense of many instances. It can be big data in the sense of many dimensions. You can have features that vary differently, some features that are categorical or that are continuous. You can have problems with heteroscedasticity, variance, noise, but variance and noise mean different things for different kinds of features, right? So noise for the Sarcasm data set is like typos, maybe, and noise for the sensor data set is the sensor doesn't work. It goes down and it misses some of the readings, let's say. So that even there, that has a lot of nuance to it. So the scaling pain points of those different kinds of data are really data set specific. So just to kind of give you a sense of what makes scaling so challenging to work across so many different kinds of data sets. What we're looking at here is a heat map where we're scaling the number of features and the number of instances. So I'm ranging between 500 rows to 5 million rows and 5 columns to 50 columns. And I'm fitting a logistic regression, scikit-learn kind of default parameters, no hyperparameter tuning or anything fancy. And I'm fitting it for every single one of those. And then the intensity of the color here is the amount of time that it took fit to complete. So you can see that even for a 5 million row data set with pretty complex dimensionality, we're done in like 10 seconds. So that's pretty good. Not all models scale that well. So here we have a deep learning model, multi-layer perceptron model. Again, it's somewhat simpler. The scikit-learn implementation of MLP is designed really just, I think, for prototyping deep learning. And obviously you would use probably something like PyTorch or Keras and TensorFlow to do this at scale. But just to kind of illustrate, with a multi-layer perceptron model, it's slower. So for 5 million instances and 50 features, we're now closer to like the 5-minute, 6-minute kind of space. Still, from what you've heard about deep learning and how it takes, weeks and months and stuff to train these models, like 5 minutes seems kind of like, like I could do that, right? And yet, as we sort of kind of expand to even more complex models, like a support vector machine, for instance, which is a very, very complex model in terms of the internal parameters, we start to quickly kind of get into a space where this becomes less and less tractable. For example, when even kind of doing this sort of demo benchmarking for this talk, I couldn't even get past 500,000 instances before my machine was like, stop. So I know what you're thinking, right? Don't use your laptop for stuff like this, which fair point. But this is really just to kind of get a sense of like, when does it become big data, right? This is where it becomes big data, right? Where it doesn't work on my computer anymore, and my computer turns off and it's mad at me. And I have to let it cool off for a little while, and I have to go cool off for a little while too. So how do you optimize that, right? So we have some options. We can be patient and just kind of let it churn for a while, kind of just let it run in the background. You can be willing to be wrong, right? Which means you can kind of like prematurely converge and say like, it doesn't have to be like, a perfect model as long as it's done because it's due tomorrow, which in industry sometimes happens. You can be rich, by which I mean have lots of AWS or Google Cloud compute resources and just kind of throw money at the problem. Or you can steer. And Yellowbrick is about steering. And so when I think about steering, I'm a cyclist, so I think about steering a bicycle, but probably some people think about steering a car or maybe a boat or something. I don't know. I think about steering a bicycle, right? So the model selection triple is a concept from, actually not from the machine learning community, it's from the databases community. And so this idea comes from a paper by Arun Kumar, who's a databases researcher. It's a great paper, and it's really about next generation databases that kind of anticipate machine learning. But the model selection triple is this sort of workflow that describes at a really high level how we do machine learning. And there's 3 phases. The first phase is feature analysis, feature engineering, and then algorithm selection, so picking the algorithm or algorithms that you're going to use to fit your model, and then finally hyperparameter tuning, so kind of trying to eke out slightly better performance by tuning the knobs. And this is sort of described as like an iterative process, right, where you kind of go through these steps over and over, and you do these triples, and eventually you stop, or you get to a score that you're happy with, and that's sort of that's how we do machine learning. And so the insight that I want to kind of add to that is that models, machine learning models, are really just aggregations of data, right? And so are data visualizations. It's just an aggregation of a lot of data. And so we should use visualizations for steering. And the promise here is that we'll be able to maybe reduce our feature space before we throw out a lot of money to run expensive grid searches. And kind of get to a better solution a little bit faster, reduce noise a little faster, identify heteroscedasticity a little sooner, those kinds of things. So I'm going to talk a little bit about some of the adventures that we have taken in the Yellowbrick development kind of process over the last 3+ years of working on Yellowbrick. So what we're looking at here is a residuals plot. So this is the residuals plot. What we're looking at is, this is a way to visualize the relationship between the values that we expected to see and the values that we actually did see when we ran a regression model. And so this is, pretty traditional kind of visualization as a way to kind of assess how effectively our regression model worked. And what we're hoping to see is a few things, right? We want to see, mostly what we want to see is randomness, right? So we don't want to see any patterns, because if there's any patterns, then our model missed something important. And we also maybe are looking for things like heteroscedasticity and stuff. But the main thing we're looking for is randomness. What's tricky about this is that when you have a lot of data, when you have a whole lot of data points, you have a whole lot of residuals. And if they're all plotted on top of each other, it's quite difficult to actually see if there's patterns or not. And so one of the things that we have introduced in Yellowbrick is a slight tweak that I think helps you scale that insight as your data set grows. And so you can see there's two kind of subtle things that we've added. One is you can see the histogram now, so we can look at the density of residuals in our scatter plot, which helps when there's a whole lot of things on top of each other. This allows you to identify that a little more easily. This was actually suggested by Ian Oswald, who, the author of High Performance Python. He's a Yellow Brick patron, and he often gives like very, very good suggestions of things that we can slightly tweak. Another thing that's sort of subtle that I'm not sure if you noticed is that the points are a little more translucent, right? So that's also another way to scale insight, is by having this alpha parameter that allows you to, kind of very delicately turn the volume down on your points, and that lets you see places where things are stacked up on top of each other. It allows you to see those patterns, or hopefully no patterns, in your residuals plot. So here what we're looking at is a parallel coordinates plot. Parallel coordinates are useful for looking to see if there are features in your data that are helping it be differentiable into categories. And so the red and the blue correspond to two classes for a classification problem. What we want to see, what we're hoping to see, assuming we want to be able to perform classification, is we want to sort of see braids or chords of activity across the plot that are all the same color. So what we see in the very top plot here is kind of the most traditional parallel coordinates. In fact, you can do the same thing in pandas and a number of other libraries. They offer, different implementations of parallel coordinates. So in that top example, what we're seeing is each point, a single row in your data set is plotted as connected line segments. The problem here is that without any kind of standardization, normalization, it's really hard to interpret a plot like this where, the features vary between different values. And so the second one under that is, with this standardization that we've added in, so it kind of makes it a little bit easier to identify if there are kind of relationships here between the features and the classes, and you can start to see that there are some, some relationships. The problem is that Yellow Brick is built on top of matplotlib, and the way that matplotlib works is it treats the figure as a canvas, right? And the way that that works is you paint a layer onto the canvas, and then you paint another layer on top of that, and you paint another layer on top of that, and on top of that, and on top of that. So if each point is a layer, and you have a lot of points, it's going to be plotting for a very, very long time. And so we found that this plot in particular scaled very poorly as data set size increases in terms of the number of instances. And so one of our contributors came up with this sort of interesting hack, which is that instead of plotting every point, first we do a classification, and then we plot each class together as if it's a single layer in the figure. And what you can see on the other side, so the right-hand side, is what the speed up factor is as your data set increases. It's essentially linear, right? So this makes it scale really well. The downside then is that you don't get to see the thickness of the chords anymore, right? And so the insight has changed a little bit, and so there is this sort of sacrifice that we have to make in order to make this performant at scale. So just some of the things that we have to kind of cope with as we think about scaling this kind of stuff. One of the most challenging kind of big data sets to visualize is a text data set. In my humble opinion, I work with text data. So one of the things that's challenging is that it's quite difficult to figure out clever ways to visualize big text corpora that are not just word clouds. So what we're looking at here is a few things. On the left-hand side, we have a class prediction error plot in Yellow Brick. And what this does is it shows us for each of the classes in our corpus, and there are 5 classes, we can see, by color, we can see where our misclassifications are happening the most often. So for instance, when we misclassify something as, let's say we're trying to classify gaming documents. Gaming is the pink kind of salmon color here. When we get that classification wrong, we're most likely to misclassify gaming documents as being either about books or about cooking. So books are the green and cooking is the blue. And so this is a little bit like a confusion matrix, but visualized as a bar chart. So then on the right-hand side, what we can see are token frequency distributions of the top 50 tokens. But what we're doing is we're just visualizing the most, those tokens from the classes where our classification performed the worst. And that's helpful because then you can start to dig in and say, what is it that kind of went wrong here when I was trying to do classification? And this lends itself to sort of a visual pipeline. So if you're familiar with the concept of a pipeline in scikit-learn, right, where you can chain together a series of transformers and estimators and treat them as a single object, you can kind of see quickly how it would be helpful to be able to do something like this with visualization because it tells sort of a complete story. Let's say where we start with some kind of rank 2D visualization of our features to look for covariance relationships, and then we do some kind of regression, we plot our prediction error, and then finally we, before we start doing hyperparameter tuning, we look to see if there are subsections of our corpus using cross-validation, if there are subsections of our data set where our classification or our regression performed worse. This journey has not been without bumps in the road. One kind of big thing is that it turns out machine learning is not particularly well suited to object-oriented programming. So this probably comes as no surprise to people who have used TensorFlow or kind of complex like graph-based models. It's really tricky, but oh well, we sort of made that decision and we went down that road. But one thing that's sort of special and I think really amazing and delightful to me about the scikit-learn API is that they kind of figured out a clever way to avoid some of the problems that you can imagine would happen doing object-oriented programming with for machine learning. Machine learning with object-oriented programming, which is you don't store X. Right? So X is not an attribute on the estimator class, right? So you are kind of storing things like the score and the coefficients and stuff like that, but you don't store the data. So our Yellowbrick API has attempted to kind of stay true to that promise. That ends up being really difficult, though, when you're doing visualizations. And so one of the kind of challenges is, trying to make this decision about if this is going to be a tool that's optimized for students or for practitioners. Benjamin and I are both teachers and also practitioners. And so we kind of have tried our best to make Yellowbrick something that can work for everybody. So for example, we have these one-liner functions, which are, in high demand. And essentially what the one-liner does is it kind of collapses a few lines of code into a single, a single call, so that you can kind of get, a plot without very much work, for busy people who don't have time to write 4 lines. But one of the problems then is what do you store? What do you store in the object, right? So do you pass the user back the plot? Do you give them the axes in case they need to make a multiplot? Do you pass back the other class attributes, like how long it took to fit the model? Those are all kind of important things, and so it's one of the sort of challenges that we've had in kind of making some of these decisions. Another big challenge, honestly, is just the tension between making progress as a library library and documenting that progress. So for example, have people heard about the plot directive in Matplotlib? It's really awesome. Basically, it's a way to, like, in Sphinx, you can kind of generate your images on demand. It's terrific unless your plot takes a really long time, like recursive feature elimination. It makes your docs build really slowly, so don't use the plot directive for that. Also, testing, as we sort of scale the library and grow as a library, our tests take longer and longer and longer to run, right? And we want to have good coverage, but that obviously is a pain point. So in terms of kind of just really quickly what's on the roadmap, one of the things that we want to do better at is get better at kind of machine learning oriented aggregation. And so I think that Seaborn does a really nice job, for instance, at this, using things like Hexbin as a way to aggregate large amounts of data in a small space without sort of sacrificing insight. Another example is using tools like brushing and filtering. So what we're looking at here is a radial visualization plot, which works really well when you only have a few features. But as you scale the number of features, it becomes less and less interpretable, and that obviously doesn't work very well. So if we could sort of brush on some of the features and brush them off, that would be kind of a quick way to be able to scale insight as features grow. We can also, I think, make a lot better use of joblib to do parallelization for some of our visualizers where you're essentially fitting multiple models, so we could kind of do a map-reduce kind of solution there. Another kind of big thing that we're going to be doing is adding sort of support for more complex multi-axis plots. So for example, the residuals plot has, it's essentially two plots now, right? It's the residuals and then it's the histogram. But let's say you wanted to do that inside of a visual pipeline, then we have to kind of add even more sub-axes to that. So the suggestion from the Matplotlib folks is to use Axes toolkit. So it's under construction. We're kind of working on that now. We're also obviously looking to other visualization libraries for inspiration. But kind of just as an overview, I think that what we're hoping is that Yellowbrick can be a way to kind of help scale insight as your data sets vary in size and complexity. And we'd be happy to have any of you contribute, join, add features, add issues to the backlog, give us suggestions about the data that you're working with. And thanks very much.
We have just a little bit of time for questions before lunch starts. So are there any questions for Rebecca?
Standing between people and lunch is
I'm
not conducive to questions.
Room for hands. It's a long, wide room. So I have a question. You had data shader mentioned on the slide, but that was not your solution for the residuals plot. Were you hoping to use data shader for the residuals plot? Large data?
I think it would be interesting to create, so one of the things that we're trying to do also is minimize the dependencies, because if people are using this kind of in a cloud-based scenario where they have to kind of do all the installation on demand, you want to kind of keep your dependencies small. But we actually have a number of visualizers that have an optional dependency, like a UMAP visualizer that has an optional UMAP dependency, so it's not required, but if you have it, then you can use that. And so I think that probably we could do some stuff around that.
Okay, let's thank Rebecca again.